Okay, we can start. So we began modular arithmetic in the last class, which will entail equations of this type, calculations of this form where you compare numbers like 2 raised to 8 with 6. Okay, so they are different numbers, but they are considered the same because their remainder by 10 is the same. Okay, so this is the mod relation on integers. And then if you square, then you can square both sides. That is clear. The remainder will remain the same, mod 10. And similarly, if you add both sides the same thing, then the integers are again the same, mod 10, right? So up to multiplication, squaring, addition, subtraction, it's consistent, or it respects this relation of congruence, mod 10 for example in this case, but in general any mod n for integer n. So definition is basically you can also say a and b will be the same mod n if a is in this arithmetic progression with offset b and common difference n. So there is a case such that a is equal to b plus kn. So this b plus kn, as k varies from minus infinity to plus infinity, this is called the residue class, right? So essentially we have clubbed together these infinitely many integers in one class. They are all considered same, which is same as b. So now there are only finitely many integers, and that class is called z/n. Okay, these are all the integers now. There are only n integers, 0, 1, 2, and n minus 1. Obviously, for a given n. If you change n, then the set of representatives will change. Arithmetic will totally change. Any questions till now? Okay, so currently this is a set z/n, but this set has it affords many operations. For example, you can add 2 elements, or you can multiply 2 elements, and you will still get an element within the set, right? So it affords addition, multiplication, again mod n. So for all AB in this set, E mod n plus B mod n is this element E plus B mod n. Right, for example, if you add 0 and 1, then you will get 1, which is again in the set. More interestingly, if you add 1 and n minus 1, right, then you will get n, but that is outside the set. So is that a mistake? Because you have to divide by n and then you get the remainder, right? So actually n will be 0. So in that sense, every sum is in the set. With fun, sorry. So this is how you will bring it back inside this set. So this is called the mod n arithmetic, in particular addition here. And similarly, minus 1, for example, right, that is not in the set, but it has a representative which is n minus 1, and so on. So which means multiplication is also fine. So you have this first property, and the second property is A mod n times B mod n is AB mod n. So which now allows also multiplication. So if you multiply 0 with anything, of course you will get 0, which is fine, which is in the set. But if you multiplied, let's say 2 with n by 2, if n was even, then that will again be n, which is outside the set. You bring it inside the set by putting it 0. So for example, you can also do 2 times n minus 1, right, which is actually minus 2, which is n minus 2. And so on. So you can multiply any two numbers and it will give you something bigger, but then you can bring it back by the remainder. So this is what Z slash n affords. I don't want to use the word here, but later on in the course you will see that such objects are called rings. Okay, so this is actually this is the most famous ring, the mod n arithmetic ring. And yeah, the RHS of these properties is clear, it's unique. There is a unique element which is a plus b, right? So this there is no ambiguity. When you add, then you will get a unique element, and when you multiply, you will get a unique element. So those things should be clear. You can work that out and satisfy yourself. Okay. Right, so another example of the type that we saw in the last class. So suppose you have to compute 2 raised to 39 mod 10, which is basically the last digit. Right, so how do you calculate this? So this is again, just doing multiplication will suffice. But in the previous class, we had done simply squaring, right? 39 you cannot get by multiplication by 2. So what do you do here? So here you can't do squaring, you have to do really multiplication. So any ideas? How can you start? Sorry? Yeah, so most systematic will be that you look at the exponent, so that you can write in powers of 2. So 32 plus 4 plus 2 plus 1. And then you can use the previous calculation from the last class, where 2 raised to 32 was 6 mod 10, right? And 2 raised to 4 was also 6. So we can actually club both of them and still get 6. So what remains is then 2 square and 2 1, which will be 6 times 8, which will be 8. Right, so here we are using squaring, but also we have to multiply, and then we get an answer different from 6. Is this clear? Any questions? So that is the mod 10 arithmetic. Gives you the last digit. So the question here is, what will not work in this arithmetic? So what about division? So addition multiplication will work. Can you also divide mod 10? So in Z mod 10, Z slash 10 set is division defined. What do you think? Is it? So for example, what is, 0 you have to rule out. Division by 0 is never allowed. But other than 0, is division allowed? Is there an example where it's non-zero in the set, but its inverse, the reciprocal will not exist for n equal to 10? It will not exist for 1 by 2. Why is that? Suppose it existed an element x, then and x is an element in Z mod 10, right? Then it has to be the case that 1 and 2x are the same, which means what? I mean, the inverse of 2 is x, so clearly 2x has to be 1, which means what? What should you do? Should multiply by 5 both sides. So you will get that 5 is 0. And is this true? So this is a contradiction. Right? The contradiction means that there does not exist an x. There does not exist 2 inverse in Z10. So inverses are not for free in this arithmetic. Okay, the problem basically happens when you are able to do this last step in the proof by contradiction. The last step is you multiply your 2 by something which vanishes, which means that 2 divides 10. So the numbers which divide n, they will not have an inverse. Is that clear? So M inverse mod n doesn't exist if M divides n. Any questions? That is what we have observed from this simple example. Sorry, what is 3 inverse? Mod 10. What is that? So 3 inverse mod 10, is it 7? It's 7, right? Because 7 times 3 is 21, which is 1. Is it fine? Yeah, so for some numbers, for some representatives, inverse is there. For other representatives, it is not there. So we can safely say that Z slash n inverse operator is absent. Or even with 0 removed, even for the non-zero elements of Z slash n, inverse doesn't exist. So it's a problem more serious than division by 0. Okay, we are not doing division by 0, but still we are not able to divide. So this is a new problem that happens in this new arithmetic. But addition, multiplication were fine. So this also means that so Z slash n doesn't have, or we can say may not have, cancellation rule. So cancellation rule means that if A times B is 0, then we cannot deduce that A is 0 or B is 0. Is that clear? So two non-zero things can multiply and give you 0. That's the problem in the Z/N set. And the example was 2 times 5, right? 2 is not 0, 5 is not 0, but the product is 0. So this cancellation rule is missing, which we take for granted in integers. Is that clear? This is exactly why you don't get inverses. Okay. And similarly, the following can also happen. A times B congruent to A times C does not mean that A is 0 or B is C. Right? So if you see this equation AB equal to AC, you cannot just divide by A, even if A is non-zero. So it may happen that A is non-zero and B is different from C, but still AB is AC. Right? So that's the cancellation rule, which is not followed in this arithmetic. Sure. Good point. Does everybody agree? Didn't want to say that, but well, you have said it. So in general, if the GCD is not 1, okay, also in the case when the GCD is not 1, then M inverse mod n will not exist. Right? So for example, so 6 inverse mod 10 is an example. So the proof of this is same as in the red calculation. What happens in 6 is that we have 2 times 3, 3 is co-prime to 10, but 2 is not. So if there was an inverse of 6, there would be an inverse of 2. But there is no inverse of 2, then hence there is no inverse of 6. Okay? So it holds as long as M shares a factor with the modulus. Anything else? Maybe we can just do some more numerical examples, since all this seems very new to you. So can you give the last digit of 5 to the n mod 10? This is 5, right? What is the proof of this? Yeah, so you can do just induction. So basically, we just have to show in the induction case that 5 square is 5. Right? So you start with 5. It is clearly 5. So n equal to 1 is satisfied. And for larger n's, if it's 5, then you multiply by 5, you still get 5. So for n plus 1 also it's true. Okay, so suppose n has these digits in base 10. So the decimal digits of n are xr minus 1 dot dot x0. It's r plus 1 digit number. So what is n mod 9? So this is one step harder, right? n mod 10 is what we have been studying. What is n mod 9? Yes, so you can see that this will be the same as the calculation sum of the digits. So why is that? So you use what was given, so you have n xr 10 to the r plus r minus 1 10 to the r minus 1 x0. Now, when you go mod 9, then all these 10 powers, they become 1. So you get sigma xi. Is that clear? Okay. And same thing you can, I mean, once you have n mod 9, you also have n mod 3. That's the same argument. What about what about n mod 2? Yeah, so this is the divisibility test that you used to read in school, right? For division by 9, you would sum up the digits. And for division by 2, you just look at the last digit. So that is what you recover. N mod 2 is the same as x0. Okay, so divisibility by 2 only depends on the the least significant digit, and divisibility by 9 depends on the sum of digits, and so on. What about 11? That used to be another divisibility test, right, which you were forced to remember. So what is that? The alternating sum. So now you are smart enough to prove it. Okay, so n mod 11 is just the alternating sum of the digits. That's the divisibility test by 11. So these things you can now recover. So now using this, you can find integer solutions of linear systems like this. So suppose you have to find integers x and y such that 25x plus 31y is 6. Can you use modular arithmetic to solve this? You want to find all the solutions for this. So what is the modulus that you should use? There is an obvious modulus to be used. You can see this mod 6, right? So if you see this mod 6, then this will be x plus y equal to 0, right? So then you learn that basically y is minus x, mod 6. So you can do that substitution, and then you can, in another step, you will get the integer solutions for this. Let me not do this. This is an exercise. And so such systems are called Diophantine equations because you want integral solutions. Okay, so integral solutions are a bit different from linear algebra solutions. So there you want real solutions, but here when you specify integral, the question becomes harder. So So how many real solutions are there for this equation? How many real xy? Sorry? Infinitely many, right? Because you can fix y anything and that fixes unique x. So there are infinitely many real solutions. How many integral solutions are there? Yeah, how do you deduce infinite? From the picture, it's not clear. So, because if you arbitrarily fix y, then 25 won't divide. So there will be no x. Right? So you have to work harder in this case. So Diophantine systems are harder. And if you want to make it really hard, then you have to go to quadratic Diophantine systems, like find x, y such that maybe x square minus 2y square is 1. Okay, these kind of systems will be harder now to analyze. So anyways, you can play with this. Let's move to this linear system more systematically. So solving linear equations. In modern arithmetic. So the question is the first question will be one variate, one unknown is there, and it's a linear equation. So how do you solve Ax equal to B mod n? Right, so as is traditional, we'll assume x to be the unknown. Everything is given, a, b, and n are given numbers. And you are interested in finding this x. So it's a linear system over constants from z/n, so modern arithmetic. How do you solve this? Any ideas? Now you should also already be able to see this. We have talked about inverse. So in case A inverse exists, then you do what? Then x is just A inverse B, or B divided by A. So that is the easy case. Right, so in case A has an inverse mod n, then x has only one solution. Right, there is a unique solution. So think okay, we should talk about how to compute inverse. How do you compute inverse actually? Let's write that down. So A inverse mod n is easy to compute, or say that it doesn't exist. So what is the algorithm to compute inverse? So obviously in the z/n, this modern arithmetic, you know how to add, you know how to multiply, because that is just addition multiplication with division and getting the remainder, right? So those things you know from school. How do you deal with this inverse? So you are given two numbers A and n. How do you compute 1 by A mod n or say that it doesn't exist. Can you can you reduce it to addition, multiplication and division in the usual sense? Division in the usual sense. So the idea will be again contained in Euclid GCD algorithm. Okay, so what you do is use Euclid GCD algorithm to write, basically you will compute GCD of the numbers which are given. So you have A and N, you apply Euclid GCD. So you will get the GCD written as Ka plus L times A plus K times N. Okay, when you do the the extended Euclid GCD algorithm, you will get this K and L. And what now? So I claim that now you have the answer. Do you see it? So suppose the GCD was 1. What is A inverse mod n from this equation? Sorry? L, right? So if the GCD is 1, then it means that L can be taken as A inverse mod n. The reason is that L times A mod n is 1, right? That is what you learn from this immediately. So what you learn is that L times A is the GCD mod n. That's the equation. So if the GCD is 1, then you know that L is the inverse of A and A is the inverse of L. Is that clear? Yes. Yeah, what is polylog n? People don't know that. Well, easy is something that a regular student in this class will code in C program, and for hundreds and thousands of digits, the program will stop in few hours. That is what easy is. It shouldn't be that the student graduates and the program is still computing inverse. That we don't want. You will not get jobs with such programming skills. So to guarantee that you get a job, that is what this easiness is. So this is an easy algorithm because even if this A and N are thousands of digits, which by the way will be happening in a lot of applications where programming is done, especially in cryptography or error correcting codes. So their N is huge, but even if it is thousands of digits, this Euclid GCD will only require thousands of steps, which is extremely fast too, which is basically a for loop. So even millions of steps of a for loop is very easy. Okay, it's very fast. So that will give you L and K. As you know from Bezier properties, L and K are also small. Right? In particular, L and K will be smaller than, at least in magnitude, smaller than N. So L and K will be small numbers, you will get them fast. And this red equation is saying that if GCD is 1, then that's A inverse. So you have computed A inverse. Okay, so what happens when the GCD is not 1? What do you do then? So GCD is G, which is not 1, which is greater than 1. So in that case, you are getting L times A congruent to G mod n, say G is 100, so you are getting L times A congruent to 100 mod n, right? So we don't know what is A inverse from this. So any ideas there? So fortunately, this even this equation L times A congruent to G mod n, it carries all the information, because G is not arbitrary. G is a number that divides both A and n, right? It divides this and it divides this. So what should you do? You should just divide out this equation by G. So what you get is L times A by G is 1 mod G, mod n by G. Fine. How will it help? If G divides L, yeah, maybe this equation doesn't help. Let me make a bold claim here. Let me say that L inverse doesn't exist. So if the GCD of A and n is greater than 1, then the GCD doesn't exist. This we have kind of proved before in the previous slide, right? We said that, sorry, not L inverse, A inverse. We had given that short proof that if an inverse exists, say x, Ax equal to 1 mod n, then you get a contradiction. So the same proof. But now we can write it down just for surety, because so suppose it exists. Suppose Ax is 1 mod n, then what happens? How do you use it? How do you use x somewhere here in these equations to get a contradiction? So what you can do is, see, what you basically want this, you want to multiply by something so that A vanishes, which means that it becomes divisible by n. So you should multiply it by, let's multiply by n by G. Okay, so let's multiply this equation both sides by n by G. So then what happens? This means that, so Na by G is what? Divisible by n, because G divides A, right? So you have 0 congruent to n by G mod n. Is this fine? Is this true? Is n by G, could n by G be 0? Since G is greater than 1 and G divides n, this is a number between 1 and n, right? So it obviously is not 0. Its value is smaller than n. So that's a contradiction, which means that A inverse doesn't exist. So that's it. That covers both the cases. So either GCD, either ANN or co-prime, in which case Euclid GCD, extended Euclid GCD gives the inverse. Directly, you just compute L and K, and L is the inverse. Or the Euclid GCD says that ANN share a factor G which is large, in which case anyways inverse will not exist by this proof. Clear? Okay. So compute, given a number, it's very easy to write down an algorithm which tells you whether its inverse will exist or not. And when it exists, it will also give you the inverse between 1 and n, between 1 and n minus 1 actually. So, okay, so now how will it help in solving AX congruent to B mod n? Right, our original goal is to solve equations in this new arithmetic. So anyways, with this, let's first define the notation which we'll use. So given co-prime AN, we denote A inverse, we use A inverse mod n to denote the unique inverse. Okay, so whenever I write A inverse mod n, then it means that it exists because A and n are co-prime, and it's also unique. Actually, that we have not shown. Why is it unique? Why can't we have two inverses? That needs to be shown. Let's add it here. How do you show that it's unique? So let's do it here. So suppose you have AX1 congruent to 1 and also AX2 congruent to 1. Okay. Then what do you get? You can take the difference, right? So A times X1 minus X2 is 0 mod n. And then what? Yeah, then you can multiply both sides by A inverse, which exists by the first equation, for example, x1. So you can multiply both sides of this congruence with x1, and that will give you that x1 minus x2 is 0. Is this clear? So when inverse exists, it's unique. So that shows the uniqueness. So that's quite straightforward. Yeah, so then we will have this definition that whenever I write A inverse mod n, I will mean that it exists, that numbers are co-prime, and that it's unique. Okay, if it doesn't exist, then we'll not use this notation. Okay. Okay, so one important example of this is A is say n is prime, n is a prime number, and n does not divide A. So in that case, what can you say about A inverse mod n? Will it exist or not? So since n is prime, can you deduce, so can A and n share a factor? Yeah, because if they shared a factor, then that factor will be divisible by n, and then A will be divisible by n, which is ruled out in the hypothesis. So this actually means that A and n are co-prime, which means that A inverse mod n exists. Which means that for the prime case, there is this good property that for every number inverse exists except 0, right? This condition is just saying that A is not 0. So in the Z/n set, excluding 0, everything is invertible, right? So that is why primes are very special. This Z/n arithmetic it's a very special arithmetic. It is basically division is also available. Only problem is division by 0. Everything else is fine. So you have addition, multiplication, and division. Is that clear? So again, I want to avoid the word, but when we come to it, we'll call it a field. Okay, these sets Z/n are called fields. So field has the property that it has addition, multiplication, and division. So it's much better than a ring. It's a ring, but it has more properties, so it's a field. Okay. Yeah, maybe we can see some numerical examples. So what is 2 inverse mod 11? First of all, will it exist? Because 2 and 11 are co-prime, right? So if it exists, what is it? 1 to 10? 6, right? Because, I mean, once somebody tells you 6, you can easily check. But finding 6 is very hard. Right now you can check that 6 times 2 is 1, mod 11. So what is 16 inverse mod 13? Will it exist, and then what is it? It will exist again because 13 is prime and 16 is not divisible. 16 is not 0. It's not divisible by 13. So first simplification you should do is you should divide by 13 to make it smaller. Right? So this is the same as 3 inverse. And what is 3 inverse mod 13? Yes, so it's 9, and again once you are told, you will see the light. Okay, what is 92 inverse mod 23? Will it exist? Yes or no? Who says no? Why? Exactly. So 92 is 0. And as you know, division by 0 is never allowed. So this doesn't exist. right? So you should reduce by the modulus, which will make it equal to 0, and then you ask for inverse. That doesn't exist. Okay. And yeah, and just this I will not do, but you can do as an exercise. You compute 25 inverse mod 23 using Euclid's algorithm. Right, so basically you have to do what was said in this lemma, that you compute the GCD of 25 and 23, which is 2 and 23. You will have some steps of divisions, quotients and remainders, and then you will get this L times 25 plus K times 23 equal to 1, right? And from there you will get L, which is 25 inverse. So you can do that manually and, sorry? No, the answer is fine, but you do the actual GCD algorithm just to see what happens. Okay. Any questions at this point? So that is a lot of new things. You can just go through this again and more examples. But meanwhile, let's state a major theorem at this point, which has many proofs known. We'll see one simple proof here. So this is called Fermat's Little theorem, which kind of belittles its importance. It's from 1640s. So it says that for a prime number p, and a number a which is not 0 mod p, right? In other words, p doesn't divide a. It talks about, for some strange reason, a to the p or a to the p minus 1 mod p. Mod p. So the value will be, didn't we see a combinatorial proof of this? Yeah. So that was another proof. Using counting, we got a proof of this, but now we'll see kind of the original proof. It's much simpler than that. I mean, you don't need these necklaces and counting, which is a bit artificial. Yeah, why is it called Little theorem? Does anybody know? Because there is a last theorem of Fermat. So compared to that Fermat's last theorem, this is a Little theorem. Do you know this last theorem of Fermat? It is not a theorem. Right? It was Fermat's conjecture. Yeah, so this is just to contrast that. Sorry? Yeah, but not by Fermat. Yeah, proof given by Wiles. Okay, so yeah, here the proof will be much simpler. You don't have to worry about the proof of Fermat's Little theorem. So what you do is, this a raised to p minus 1 suggests that you have to multiply p minus 1 things to get to this value. So what are the p minus 1 things that you will multiply? I mean, you can obviously multiply a with itself, but that is kind of the original question, so you will not get anywhere. So you have to multiply something which is more interesting than just multiplying a many times. So what can you do? You multiply A with 2A with 3A with 4A and so on. So let's consider the set S where numbers are A, 2A, 3A, P minus 1A. And we are interested in them as mod P, right? Because we only care about mod P arithmetic in the whole proof. So the numbers are integers are bigger because they are being scaled up by A, but then you can divide by P and we are looking at the remainder. So that is the set S, and we are interested in their product. So what is this? Right, so the elements of S, when you multiply them, what do you get? Yeah, why do you get P minus 1 factorial? So what you have to realize is that S has P minus 1 distinct elements. No two elements are the same mod P. So that's the proof. So what you show is if IA is the same as JA mod P, then I and J are the same. But I and J are not the same, right? Because we have taken I and J between 1 and P minus 1. So I, J are always different. So which means that the size of the set S is exactly P minus 1. So that's a consequence of this. Size of S is P minus 1. How do you prove this? So if IA and JA is the same, then you get then it means that I minus J times A is 0, which means, yeah, then we have seen many times before that A inverse mod P exists, and so I is J. Right, just from that, I mean, we could have said this directly also. We are scaling up by A, but A inverse also exists, right? So the scaling is just permuting the elements 1 to P minus 1. So S is just, I mean, if you think of S as an ordered set, then it is simply a permutation of 1 to P minus 1. So with that observation, what do you learn about the set S? That it's exactly 1 to P minus 1, which is basically it's Z slash P minus 0. Okay, so S is everything in Z slash P except 0, of course. Is that clear? So now let's get back to this product. What do you learn about the product? So the product of A, 2A, 3A dot P minus 1A, mod P is what? Well, you can permute it back, the product remains the same. So it's P minus 1 factorial mod P. And what do you get from this? So now comes the interesting thing, that left hand side is nothing but this. Right, so left hand side is just, it's a scaling everywhere, so it's a scaling factorial by e to the p minus 1, which means what? So is p minus 1 factorial co-prime to p? It is, right? P cannot divide it because the factors are all very small. So which means that you can multiply by the inverse, the cancellation rule, and you have a raised to p minus 1 congruent to 1 mod p. That finishes the proof of Fermat's little theorem. So if, as long as a is not 0 mod p, multiplying it p minus 1 times, you get 1. 1 as the remainder. Any questions? Okay.